Why is swarm robotics coordination difficult? Imagine trying to organize hundreds of tiny robots to work together smoothly without a boss telling them what to do. That's the challenge at the heart of swarm robotics. These systems relying on many small robots working as a team, but they do not have a central controller. Instead, each robot makes decisions based only on what it senses nearby and the signals it receives from its neighbors. This makes coordinating their actions tricky because there is no single robot guiding the entire group. One big problem is that each robot only has local information. It cannot see the whole picture, so it has to guess what the rest of the swarm is doing. This makes it hard to coordinate complex tasks like covering a large area or tracking a moving target. As the number of robots grows, the communication demands also increase. Sending messages between thousands of robots can overload the system, causing delays or lost data. The algorithms that manage this need to be very efficient to handle all the messages without slowing down. Communication is another challenge. These robots often talk through signals or environmental cues rather than constant direct links. Their communication range is limited, and bandwidth is often low. This means they cannot share information quickly or in large amounts, which makes it harder to keep everyone synchronized. If one robot misses a message or cannot communicate well, it can throw off the entire group's coordination. Balancing local actions with global goals adds to the difficulty. Robots need to follow simple rules that lead to the overall mission, like spreading out evenly or gathering at a point. Designing these rules so they work well in all situations is tough. If the rules are too simple, the robots might get stuck in loops or fail to adapt when conditions change. If they are too complex, the system becomes hard to manage and slow. Robustness is vital for real-world use. Robots face unpredictable environments with obstacles, weather, and sensor noise. If a robot breaks or malfunctions, the swarm must still keep working. This requires algorithms that can handle failures and reassign tasks quickly. Otherwise, the whole operation could fall apart if one or two robots stop functioning. Many applications demand quick decisions. For example, search and rescue teams need robots to respond fast in dangerous situations. Achieving low-latency decision-making across hundreds or thousands of robots is difficult because of limited processing power and communication bandwidth. It's a balancing act to keep everything running smoothly in real time. Finally, the environment itself complicates things. Swarm robots often operate in unstructured, changing settings like forests, disaster zones, or busy streets. Terrain irregularities, weather, and obstacles make coordination even harder. Simulating these conditions accurately is tough, and designing systems that can adapt on the fly is an ongoing challenge. In real-world uses like farming or traffic control, these challenges become very clear. Swarm robots must coordinate over large fields or busy roads, often with limited signals and unpredictable conditions. They need to work together efficiently without a central boss, which is why making coordination work is such a complex puzzle. It involves managing many robots, limited communication, environmental hurdles, and the need for quick, reliable decisions. That's what makes swarm robotics coordination a fascinating and active area of research.